All right, in this video, we're going to work an example problem related to calculating the amount of work done in a process. So work done in the physics sense, the technical physics sense, where work is equal to a force times a distance. Specifically, it's the force times the distance over which that force acted. And so this is a calculus course. It's not a physics course. And all the calculus textbook is doing here is it's using this concept of work to illustrate the idea of using integration for some real life scenario. And so when you get down to the idea of calculating the work done in the most general sense, well, then you could have potentially 3 dimensions. And then the force vector doesn't always have to be in line with the displacement vector, okay? But here in single variable calculus, we're looking at simplified cases where it's one-dimensional. So we're going to have just motion along a straight line. And so along a straight line, you have, the positive direction or the negative direction. And a lot of times we're only going to consider the positive direction, or like one direction. So the motion is along a straight line. It's not like 2 or 3 dimensional. And then also the force that we're considering, it always, the direction of that force is always along that same line. And usually it's not only is it going to be along that same line, it'll be always in the same direction as the displacement. Okay, so we're not considering the idea of, okay, maybe the force vector is off the direction of motion. So it's a simplified case. But in general, what we're considering is that, so for all these problems that we're going to do for integrating to find work, it's motion in one direction. That direction can potentially have positive or negative coordinates, so positive and negative directions. The velocity could be positive or negative. The acceleration could be positive or negative. And then the force will always have a direction along this line, and it could potentially be, the force could be positive or negative. So it could be in the same direction as the displacement or in the opposite direction, in which case that would be like a negative work done. If the force is in the opposite direction of the displacement, then that's negative work done. Okay, and so with that, we want to calculate the amount of work done in a process. And so what's going to happen is, in the simplest case, the force would be constant over the entire displacement. But what we're studying in this section is the idea that potentially the force isn't constant. And the way we thought about approaching this was that, so if you know an object's position with respect to time or just whatever, you know the object's position over some interval from one position to another position, then you can think about the idea of breaking down that position interval into a bunch of pieces of equal width. And so each of those pieces would be like a little displacement. And as the number of these pieces got large enough, each displacement would be small, so that you could assume that, since it's so small, that you could assume the force acting on the object is constant over that displacement interval. And so in that small displacement interval, you could say the work done is that constant force times that displacement. And then you could add up all of the work's done in those intervals to get the total work done from position 1 to position 2. And this process, though, is exactly what we do in integration. So if you've got the position of an object, we're just talking about like straight line motion here, going from some position 1 to position 2, position A to position B, as you have it as a function of time or whatever. And then with that, you can also get an expression for the force acting on the object as a function of position. Then the idea of breaking up the position, going from A to B into pieces, into these little displacement pieces, and then assuming a constant force over each displacement, because those pieces are small enough, and then adding up the force times the displacements, that you're integrating this function here. That's exactly what you're doing. We can look at this graphically. This is an area under the curve problem. This is the force. This is the position. Again, this is simplified straight line motion. We're going from A to B. So you're breaking up, going from A to B, you're breaking this up into pieces. The position of the object, you're breaking this up into these pieces. And so what you get is, you've got this displacement here, this delta x here. It's a small little amount that the particle moved. and it's small enough that you could assume the force is constant. That's what we do. That's what the rectangles are. You're assuming a constant independent variable for each rectangle. That's integration. And so what you can see is that the work done is the area under the force versus position curve. The work done over an interval from A to B is the area under the force versus position curve. And just the main idea of looking at this concept of work from an integration standpoint is that you can see that we've kind of brought the area under the curve idea more to life here. We've really related like this physical idea of calculating work, this force times distance, and shown how calculating that is directly related to integration. All right, so let's take a look at this problem. A thick cable, 60 feet long and weighing 180 pounds, hangs from a winch on a crane. Compute in two different ways the work done if the winch winds up 25 feet of the cable. So the first, we're going to follow the method of example 4, and then second, we're going to use this method here where we write a function for the weight of the remaining cable after x feet has been wound up by the winch. Estimate the amount of work done when the winch pulls up delta x feet of cable. So, all right, we've got this 60-foot long, 180-pound cable that's hanging from a winch. So I don't know how, let me see if I can draw like a winch here. Like that with some, like a roller with some motor attached. And then you've got, 60 feet of cable hanging. All right, we'll say like this is the x direction with the origin at the winch. Once it's lifted up into the winch roller. Okay, and so there's the 60-foot long, 180-pound cable, and it says compute in two different ways the work done if the winch winds up 25 feet of the cable. And so the first way that we're going to use is the method of example 4. And so what example 4, the idea behind example 4, and this is a little bit different than example 4, so we'll have to be careful. But when I say it's different because example 4, this would be just like example 4 if it said that compute the work done to pull up the entire cable, all 60 feet. Okay, but so what example 4 did was so like you can't just, let's say we're trying to compute the work to pull up all 60 feet. You can't just say, okay, well, 60 feet times the weight, 180 pounds, because it's more complicated than that. Because as you're pulling up the chain, there's less weight that the winch is pulling up, right? So the force is changing, and kind of the distance is changing as well. It's kind of confusing. And so what example 4 did was it said, okay, let's take like 60 feet divided by n being we're going to break this cable up into n pieces. They're going to have equal width delta x. All right. Now, so within each piece, you want to know what's the weight of the chain within that piece. And that would be, so how do you know the weight of chain within each piece? Well, you say, all right, well, this chain weighs 180 pounds divided by 60 feet. So it weighs 3 pounds per foot. So you can multiply the delta x times 3. But breaking the chain up into pieces, it's not that it allows you to say that the weight is constant, because the weight is the weight. I mean, you just multiply it times the length of the piece. What it's helping with, what the pieces help with is that, so if you just broke this up into 6 pieces, so you did 60 divided by 6, that's 10 feet per piece, right? You had these big wide pieces. Okay, you still got the right weight because you're going to do 3 times 10, but then the problem comes in that you're lifting it up, and then the front half of this piece gets rolled up into the roller, and then and it takes a little bit for the bottom half to get there. And so, yeah, I guess you could assume you're lifting it up, from the midpoint, but that's the confusion then, right? That's the whole, if we were going to do that, then why not just start with, we'll do the 180 pounds times 30 feet, right? Why can't we just do that then? If we're going to assume that, okay, the width of this piece, you have the length of cable that was lifted, and we're going to multiply that you have the weight of cable that you found by the length of this piece times 3 pounds per foot. Multiply that times the coordinate of the midpoint. If we're going to do that, then why don't we just start with, okay, just do 180 pounds times 30 feet, right? But we don't know if that would work or not. So the main advantage of breaking this up into pieces like this is that as you increase the number of pieces, this delta X gets smaller and smaller. Then if it gets really small, then as the front half of the piece gets rolled up into the winch, then almost instantaneously the back half has been rolled up. So then you can say that the weight of the chain in this piece, which is 3 times delta X, times like the coordinate of this piece is equal to the work done to lift that piece. And that's a good assumption, especially as N gets really large. And then all we did was we just, for example 4, that's exactly what was done. And so you had the work done on each piece was equal to, it was delta X times 3, or 3 delta X. That's the weight in that piece. And then how much was that lifted? Just the X coordinate of the piece, right? As N goes to infinity, that X coordinate, it doesn't matter if you use the front point or the back point or the midpoint. And then that's what then we just took, then we summed all these WIs, but then we did the infinite sum and took the integral, and the integral was from like 0 to 60, and you got the work done to lift the entire chain. But this is a little bit different here, because they're only saying we're lifting up 25 feet of the cable. So we have to be a little careful. We're still going to use the same method where we're going to break up the chain into pieces, and then each of those little pieces will have a weight of chain given by 3 times the width of the piece, delta X. And we're going to use that. We're going to use that same method, but how do we account for the fact that we're only lifting up 25 feet? Well, what we're going to have to do is, so here's about 30, so this is about 25. So everything below 25 feet, it's going to be easy to calculate all the chain that's below the 25-foot mark. It's going to be easy to calculate the work done to lift it. Why is that? Because think about it. All we need to do is say, it's 60 feet, so that would be 35 feet. 35 times 3 pounds per foot is what? That's 110 pounds. Okay? All we're doing is we're lifting this 110-pound cable here 25 feet. Like, we don't need to do integration here. This times 25 feet. Right? 2750 foot-pounds. Right? Think about it. When you go from, when this gets lifted 25 feet, there is no issue. We don't need integration, because there's not like a portion of this is the weight gets taken out, right? The whole main issue of this problem has nothing to do with this lower 35 feet of cable. It's just this is 110 pounds of cable that gets lifted 25 feet. Because think about it. Let's say we did do the integration, right? We had each of these was broken up into a little piece like that. The whole point of the integration is that it's the X variable, right? It's the fact that it's the fact that this front piece is going to have a different X variable than the other pieces as far as how much it's lifted. That's the main purpose. Well, for this lower half, there is no X variable. It's 25 feet. This goes from here to here. This goes from here to here. They all go up only 25 feet. This is different. For this portion, not every single piece is being lifted 25 feet, right? This piece is being lifted 25 feet, but this piece is being lifted 13 feet. This piece is being lifted 3 feet. You see? So to lift up 25 feet of cable, you're going to have to do 2,750 foot-pounds of work to lift this bottom half. So now how much work is going to need to be done to lift this top, or not the bottom half, but the bottom 35 feet. So how much work is going to need to be done to lift the top 25 feet? Well, that's what we're going to use the method of example 4 for. So we're going to do the work done to lift one of these little pieces is, it's 3 delta X times X. So 3X delta X. Okay, so the the total work done, when we're just talking about to lift this 25-foot piece, is equal to approximately equal to the sum from I is equal to 1 to n of 3x delta x. I mean, so the delta x would be, 25 divided by n. We're not going to go into the actual limit definition. So n is the number of pieces, and so the work is exactly equal to the limit as n goes to infinity of this sum. Okay? And you can turn this into an integral, and so we're going from 0 to 25, 3x dx. Okay, so this is 3/2 x squared from 0 to 25. So 25 squared times 3 divided by 2. 937.5. Okay, so the total work done to lift this entire chain 25 feet is this plus this. Let's just round that to 3,688 foot-pounds. Okay. All right, now let's use this second method. Write a function for the weight of the remaining cable after x feet has been wound up by the winch. Estimate the amount of work done when the winch pulls up delta x feet of cable. Yeah, so this is valuable because it shows you how this is a different way of approaching the problem, and you get the same answer. So it just shows you the like the flexibility of integration. And it's nice to work problems like this with these different ways because you get more practice thinking about how to set up integration. So what they're saying here is the way we're going to think about it is you think about a piece is right. The front of the front of the piece is right at the where it gets pulled into the winch. And then, the delta x is, as the number of pieces gets larger and larger, the delta x gets smaller. So there's a little piece. And so the weight of this piece, though, is not going to be delta x times 3. The weight of this piece is going to be like x, the remaining x, or we have to define this correctly, but the remaining length of cable times 3. And so so then the winch pulls in that little piece, that tiny distance, times the remaining length of the cable times 3. Then the next piece comes and it pulls it in that tiny distance. So you would multiply to get that tiny distance would be delta x or dx times, and then whatever length of cable is remaining. And you would add all those up until you get to 25 feet, and that would be the work done. And this looks like it'd be a little nicer because it would, we could just have a formula that we plug in the work done to pull in 20 feet or whatever feet. We could calculate it. Once we have this formula, we can put in 10 feet. So the work done to lift up 10 feet or the work done to lift up 40 feet. How do we get it says at first to do this, we're going to write a function for the weight of remaining cable after x feet has been wound up by the winch. And so, this is just going to be, it's going to be a linear function. We'll say W, this is part B. We'll just say W of x, weight, and this is the weight of remaining cable after x feet has been wound up by the winch. So when x is equal to 0, it's going to be 180, right? Because there's 0 feet has been wound up by the winch, so it's 60 times 3, and then just minus 3x. So when 25 feet has been wound up by the winch, then you're subtracting 25 times 3 from 180. Okay? And this is definitely a linear function because, well, think about it. The only way it wouldn't be linear, if it wasn't linear, if we didn't say it was linear, then that would be like saying, so we wind in the first 10 feet, and the weight of remaining cable is this amount. But then you wind in 10 feet, and that means you've removed a certain amount of weight from the cable, right? You wind in another 10 feet, and now you've removed a different amount of weight from the cable. Well, that makes no sense, right? It's like a homogeneous chain. All right, so there's the WX, and now it's saying with this, we want to estimate the amount of work done when the winch pulls up delta x feet of cable. And, we're going to be able to use this to find work because this is like a force as a function of a position, right? So we can have, it's like when we do a delta x, it'll be a force times a displacement. So that's work. So if you're calculating work, then it comes down to you're going to be dealing with a force as a function of position, to where then like the delta independent variable is a displacement, and you have like a force times a displacement you're working with. All right, well, what would be for these little pieces here, what's the, okay, I shouldn't have called this W. We'll say, we'll just put M, like kind of like for mass. All right, so W of I is, so the work done for like, the idea is, so you haven't wound in any cable. Then the first piece you wind in is the ith piece. The second piece is the first piece you wind in is the first, right, W of I, a W of 1. Second piece is W of 2. Third piece, W of 3, all the way to the end. That's what the ith piece means. So Wi is what? It's just the weight as a function of x times delta x. And this makes sense because, I mean, yeah, I guess each piece is going to have its coordinate, right? This piece has its x coordinate. This piece has its x coordinate. And so when that piece gets to the winch, so this piece is 20 feet. So in this is the 11th piece, 12th piece. When this gets to the winch here, then it's x of 20. So that's 60. 180 minus 60 is, it's 120 pounds that are beneath that piece, including that piece, whatever you want to look at it. I guess it would be beneath and including that piece. Yeah, 120 pounds, right? Times the distance that the winch pulls it in, delta x. Okay, so you create the Riemann sum here, take the limit as that sum goes to infinity, and the work done is equal to, now we are calculating this just for 25 feet, but in this case we wouldn't need to like do two separate process. Like for part A, we had to first calculate the work done for this below the cable below 25 feet, but it won't matter here, right? It's all accounted for in this integral. But if we want to get this delta x, this function as a function of delta x, we could do from 0 to delta x. And then 180 minus 3x dx, right? And we'll get and what does this mean? Because what is delta x? If we did like 0 to 25, we'd just be integrating the work done to pull in the first 25 feet. And so we'll just have it as a function of delta x. So, okay, it's 180x minus 3/2 x squared, 0 to delta x. All right, so this is 180 delta x minus 3/2 delta x squared. And then we plug in 0. So yeah, that should be it. W of delta x. Okay, so this is the work done for when the winch pulls up any amount of feet. So we still want to get the answer to the question. So what is W of 25? It's, okay, 180 times 25 minus, well, let me do this. 3/2 times 25 squared, that minus that. So 3563 foot-pounds. Now comparing that to part A, this is 3688. So why wouldn't they be the same? I mean, it's close. So I wonder if it has to do with this here. Did this need to be integrated? Oh, wait. Okay. So 35 feet times 3 is 105. This is 105. Okay. So this is 105, and therefore, right, because we're lifting, this is 35 feet, lifting that up 25 feet. So 105 times 25 is 2625. All right. And then in that case, you do 2625 plus 937.5, 3563. Okay. There we go. Now they're the same. There we go.